Let's see resistances in series. The connected resistances are said to be in series when a potential difference that is applied across the combination is the sum of the resulting potential differences across the individual resistances. The current through each resistor in series is necessarily the same, but this is not the sufficient condition for resistors in series. The condition becomes sufficient when the current through each resistor is the same as the current through the terminals of the network. Figure A shows a combination of three resistances R1, R2 and R3 in series. The current through each resistor is the same as the current I through the terminals A or B of the networks. Suppose that V1, V2 and V3 are the potential differences across R1, R2 and R3 respectively. If V equal to VA minus VB be the potential difference across the network, then according to the definition of series combination, V equal to V1 plus V2 plus V3 equal to IR1 plus IR2 plus IR3 equal to I multiplied by R1 plus R2 plus R3. Therefore, R equivalent equal to V upon I equal to R1 plus R2 plus R3. Let's see some important points. Total potential V is divided in such a way that V1 is to V2 is to V3 equal to R1 is to R2 is to R3, or V1 equal to R1 upon R1 plus R2 plus R3 into V equal to IR1, V2 equal to R2 upon R1 plus R2 plus R3 into V equal to IR2, V3 equal to R3 upon R1 plus R2 plus R3 into V equal to IR3. If R1 equal to R2 equal to R3, then V1 equal to V2 equal to V3 equal to V upon 3 and R equivalent equal to 3R. Similarly, if there are n resistors in series, R equivalent equal to R1 plus R2 plus dot dot plus Rn, V1 equal to R1 upon summation Ri V, V2 equal to R2 upon summation Ri from I to n, from I equal to 1 to n, V dot dot Vn equal to Rn upon summation Ri from 1 to n into V. If R1 equal to R2 equal to dot dot equal to Rn, then V1 equal to V2 equal to dot dot equal to Vn equal to V upon n, and R